Abdullah from Group 8, Section 3. Our project name is Network Packet Transmission Monitoring System, and we are working on set 1. So let's start the presentation. Introduction. Basically, our project is about the system which secure and efficient data transfer between the two computer labs. It has the functions of MUX, DMUX, flip-flops, comparators, and counters to regulate the overseas data flow. So this is the introduction of our project, and the overall design and process is all about the power on computer, fulfill the clock enabler conditions, ensure the power on. Here you can see the block design of our project. You can see the four out inputs and 3 outputs there, and this is the flow chart of the entire process of our project. So here you can see that in the instruction manual we can see that we have to follow a certain conditions to fulfill the output. In the enabler condition, we have to follow that each labs are power on, and we also need to see that it is set to ready TRX on, set the source and destination, set max by transfer, and set pre-bar then clever to 1 and enter the passcode. If all these conditions are fulfilled, then it will run and simulate by transfer by showing each clock change using push button. And last is enable the clock to see the fan in the display. Okay, so after that, the instruction, we have the secured access process, which is basically the security system. Our system ensures and control the efficient data transmission between two computer labs. So the key component used is multiplexer, demultiplexer, multiplexer in lab A and demultiplexer in lab B. So it syncs with AND gates and ensures the data transfer happens only when all conditions are met. So in the security and mechanism passport authentication system, the major feature of our system is a 4-digit passcode to require to start the system, and the passcode and the password comparator consists of 4 comparators. Each comparators 1 digit of the entire passcode to store system passcode. If all digits are matched and the AND gate activated the clock, enabling the data transfer. If any digits are incorrect or like false, a NAND gate triggers a failure notification, and which will not process the entering process to the system. So this is basically only the authorized user can active the system. So the next slide is the multiplexer and demultiplexer that I already told that in lab A we have multiplexer, in lab B we have demultiplexer, and to sync the control enabler we used an AND gate. Here you can see we used an AND gate. Here is a multiplexer which is number 2, and demultiplexer is number 4. So we used an enabler here which is sync data, which is core cable in number 3. So this is the part where the lab A and lab B communicate with each other. So the next slide is about the powering, computer, and sync control. As you can see in the picture, we have like 3 part of this circuit, and the data transmission to begin, specific conditions must be met. Okay, so the first condition is the data must be powered on, and the second condition is data must be available to transmission, and the third one is a sync control enabler, which is the AND gate, ensures all the required conditions are fulfilled before the data transfer happens. So once all the conditions are met, data packets are sent through the coaxial cable from lab A to lab B. So this is the basic thing to powering computer and data generation sync control. So in the next slide, the multiplexer, demultiplexer, we have explained that how flip-flop and counters and computer tracks the data flow. In the process overview, you can see the data is transmitted through multiplexer and demultiplexer after selecting the correct source and destination. And a computer constantly checks the number of packets sent to if the maximum packet limit is reached, then the transmission stop automatically. Okay, so the next slide is the max packet allowance we explained now. So basically the maximum support of a multiplexer will depend on the data, and the selector inputs like S2, S1 or S0 determines which computer is active. And in the multiplexer, we select lab A, and the multiplexer we select lab B. And then we in the part B, bit transfer count and tracking data flow, we have a JK flip-flop. We can see that flip-flop, we used 3 flip-flops in the project, where it tracks the total number of bits transferred, update on each clock cycle, and stops the data flow when the preferred limit is reached. So you can see the state diagram where the first stage was 0, 0, 0, and then it continuously goes through, and the final one is 1, 1, 1. So this is basically the state diagram of our project. So the next part will be explained by our next team member, IMTIAJ. So IMTIAJ will explain from the slide 11. Thank you.
So Assalamu alaikum, doctor. This is IMTIAJ AHMED. My part is, we will start from here. So firstly, this is the flip-flop transition table and JK excitation table together. Here we have shown the system activates only if 5 conditions are made, basically. If firstly the transmission enabler is on, then computers are powered on. The third condition has to be like correct passcode is entered, then TRX clock is activated, and the maximum packet limit is must not exceed. And if all conditions are met, now the clock enabler allows data transfer. If any condition fails, transmission stops. So we'll go to the next slide. So this is the K map, which shows the successful data transfer and the system control. And the clock enabler ensures the data transmission happens only when all conditions are satisfied. So basically what happens here is during the data transfer is clock remains, if the clock remains enabled and output is set to 1, and the second it has to be data moves from lab A to lab B efficiently, and if any condition fails, transmission stops immediately. Then we'll go to the next slide. So we can see this is the complete counter circuit that we've used. Next slide. So this is the total system activation and tracking. System remains active is clock is active, and there are some key points to show as well. Clock enabler is implemented using a 5 input AND gate, and there's logic implementation. Here we using the AND gate, and the outputs 1 only when all conditions are met, and enabling the system clock, and it ensures the synchronized and controlled data transmission, preventing unauthorized access or system failure. And down we can see that the clock enabler is a 5 input AND gate, basically this one, and it ensures synchronized data transmission by activating the clock only when all necessary conditions are met, and it verifies also 5 factors that we have already talked about. And in the next slide, we can see the clock enabler of 5 factors all must be active high to enable the system activation. And we have shown the 3 parts like TRX enabler activated when user has enabled transmission. This is on the left part, and in the middle we have shown that power on computers and both source and destination computers are on. And in the right hand side, this is the clock enabler. This is about the clock activated and push to transmit signal is triggered. In the next slide, you can see that the clock enabler working when all conditions are basically satisfied. And the correct passcode has to be there, and max counter comparator ensures packet limit must not exceed. So in the next slide we can go. We have used the passcode here 1212, and we have shown that if the password is right, the lights are on and the data flowing, and if the password is wrong, the wrong password light is getting on and the data must not flow that time. And we can go to the next slide. This is the successful data transfer, the picture of it, and the clock enabler we have shown, the condition input lab B on, and all this thing, all the circuit is basically on and it's working. So we can go to the next slide. So this is the conclusion part. So we have successfully built a digital logic based monitoring system for secure packet transmission. There are some strengths, there are some limitations obviously. Strengths are secure authentication with passcode system, efficient data tracking, and then real-time monitoring through dashboard. And there are some limitations as well, like transmission is limited to 1 bit per pulse and it is slow, so no error detection mechanisms like parity checking is also a limitation. And future improvements, we have made a section of that as well. It is implementing error correction mechanisms. We'll work on that in future, and increase transmission speed using parallel processing and expand the system scalability for multi-lab support. So this was all about our project, and thank you very much.